Hello everyone, this is Shane here, back at it again with another EE140 example problem. This time we are doing a exam problem from spring 2016, midterm 2, number 1. The problem says a long coaxial cable of radius A is carrying a non-uniform current density which is equal to alpha r squared in the z direction, which is into the page. The outer shield is a grounded conductor, and a dielectric epsilon r is filled between A and B. And in between B and C, the magnetic field is equal to 0. So the first question is asking, what are the magnetic fields inside the cable? And the second is asking to solve for the current density when R is equal to A and R is equal to B using the boundary conditions. So a little outline before I start the problem. I'll be going over how to recognize an Amperes loop, how to use Amperes Law, how to solve for current density using the boundary conditions, and any extra tips I can give you guys for these type of problems. Okay, so first I'll show you how to recognize an Amperes loop problem. So there's two conditions to make sure that you can use Amperes Law in a efficient manner. So the two conditions are as follows. The magnitude of B is uniform on the contour, and the direction of B lines up with the contour, so the dot product is always equal to 1. And so the magnetic field is going to be due to the current that's flowing within the coaxial cable. So outside, here I've drawn the coaxial cable with the radius A, and outside it, let's say like outside here in this region's not gonna affect the magnetic field because we know that Ampere's law is as follows. B dot dl is equal to mu naught and the current inside. This is Ampere's law. Alright, so you're gonna ask, well Shane, how do we know if this is an Ampere's loop? Well, as the first statement says, the magnitude of B is uniform on the contour. So we're going to choose the typical element to be a ring. And for the ring, we're going to create more and more rings, each incrementing by radius r up until we meet the end of the coaxial cable, A. And for each of these rings, so this ring here, it's going to have the same magnitude of B for every part of the ring. So anywhere along this ring, so let's say point here, point here, point here, it's all going to have the same magnitude of B. And that's due to the symmetry that it has. Because this is going to be the same radius r. Okay, so we have met that requirement. The second requirement is that the direction of B lines up with the contour, so the dot product is always equal to 1. Okay, so what is a dot product? Well, the dot product, the basics of it is that vector A times vector B is going to be equal to A times B, the magnitude of A and the magnitude of B multiplied together, times the cosine of the angle between them. So if I draw two vectors, this is A, this is B, this is going to be the angle between it. Well, here we need cosine theta to be cosine of 0, so that's equal to 1. And here we can see that the magnetic field is going to be pointed outward in the radial direction. And we see that the dl portion of the Ampere's law is going to be also pointed in the same direction. So these two vectors are pointing in the same direction for everywhere along this certain ring. And so, since there is no angle between them, the cosine portion is just going to be 1. And so, using Amperes Law, we have that instead of the integral of b dot dl is equal to mu naught I inside, instead of this, it'll simplify to b times L is equal to mu naught inside. And since the typical element that we chose was a circumference, instead of L here, it's going to be b times 2 pi r is equal to mu naught I. And when I write mu naught I, I'll be referring to the current within the coaxial cable. Okay, great. So we have now established that this is indeed an Amperes loop problem. And now we're going to start solving for the magnetic field inside the cable. So this is going to be the formula or the equation we'll be working with. And so let's find the magnetic field when the radius is less than a. And so to do that, we'll use the equation above times 2 pi r is equal to mu naught. And what is current? Well, we are given the current density, and the current density is just amps per meters. So we're going to multiply by the change in the typical element, so that when we have amp per meter times by the distance, we'll just get amps, or just the current. So here, we're going to plug in the current density. Current density is alpha r squared. And then typical element we chose is circumference. And we're going to take it from all the different radiuses up until a. So that's going to be an integral. And we're going to make some room. The integral will be from the bounds of 0 to r. And what this means is that r will be any distance up until a. And so, solving for this, we have b times 2 pi r is equal to, and the integral of this is really simple, and that's the benefit of using Amperes Loop, is that it simplifies the calculations for the user. Alpha and the other constant is 2 pi, and the integral of r cubed is just r to the 4th divided by 4. Divided by 2 pi r, we'll get that the magnetic field is going to be equal to mu naught times alpha. The 2 pi cancels out, and so does the r cubed divided by 4. And this is the magnetic field for the radius r is less than a. So I'm going to move this real quickly, because now we are going to solve for the magnetic field for when r is greater than a and is less than b. So I'm going to erase this here, and now we can use the same equation still. So we'll be using this equation still for r is greater than a and less than b. But the main thing that's going to change here is that our bounds of integration is going to change. We see here that the coaxial cable is only up until radius a. So this part that I'm circling, this part is where the coaxial cable here. And the outer part is a grounded shield. And for the Amperes law, it's only using the current within the coaxial cable, so inside. So instead of it being from 0 to r, our new limits of integration is going to be from 0 up until a, because that's the full coaxial cable. Okay? Oh, and I forgot the current density. Don't forget the current density. We still have alpha r squared times that by
2 pi r and the dr. And so from here we can solve for this. So we get that this side is going to be equal to 2 pi, sorry about that, it's going to be equal to 2 pi mu naught alpha a to the fourth divided by 4. And if you divide by the 2 pi r, we'll get the magnetic field to be equal to mu naught alpha a to the fourth divided by 4r. And I see now that I have forgotten to include the direction, and the direction is going to be in the radial direction. So here I have that, and don't forget it here for the A as well, because this is going to be the magnetic field pointing outwards from the coaxial cable. And for the radius between B and C, we are already given that that's going to be equal to 0. So now, putting it all together, I have already the magnetic field from when the radius is less than A, and from when the radius is greater than A but less than B. So I'm going to put those two aside over here and erase the other part so I have more room to solve for part B. So I'm going to erase all of this. Just give me 1 second. And on here, I'm just going to check off what we have already done. So we already know how to recognize Amperes Loop. And we also know how to use Amperes Law in conjunction with Amperes Loop. And the next part is now to solve for part B, and that is the... Okay, so now I'll be solving for part B. Here, as you can see, I've already written out the formula for the boundary condition, which is N2 hat cross H1 minus H2 is equal to the current density. So for the first one, I'll be solving for when the radius is equal to A. And for H field, remember that the H field, the H field will be equal to the B field divided by the free space permeability. Okay? And here I have labeled the inner coaxial cable H1 and the outer coaxial cable H2. And first I'll solve using this labels, and after I'll show if switching the labels will change the answer. And since we have this as our labels, N2 hat is known to be the normal vector of the second median going into the first. So in this sense, since we have the outer portion being H2, it'll go from, sorry about that, our normal vector will go towards the center from H2. Okay, just give me 1 second. Just need to get my charger. Okay, sorry about that. So this is going to be our N2 hat. And that we can label as negative R hat, since it's going towards the center. Okay? And we'll have that cross H1. H1 is going to be alpha, and since we have R equal to A, we'll have A cubed divided by 4. And this is in the radial direction, remember that, minus, what do we have? H2, and H2 is still, radius is equal to A, and so that H field is still the same. Alpha A cubed divided by 4 in the radial direction. and that's going to be all equal to the current density. And these two will cancel out, and we'll just have 0. So the current density for when the radius is equal to a is 0. Okay, so what if we switch that around and our H1 was the outer ring? So I'm going to do this portion in blue so we can see. We'll make some room. So let's say this one is H1 and this is H2. Well, we can see here that what changes is that instead of our normal unit vector being negative r hat, it's going to be positive r hat since it's going outwards. Because remember, n2 is going to be from the second medium into the first. And that will be that cross. And what do we have? Well, our values are still going to be the same for h1 and h2. So we can see that already if I write this out in the radial. Minus that. I know this is a little tedious, but I'm showing this just for you guys. This is still going to be equal to 0. And so we have the same answer. It's more so as whichever one you label as your H fields, you have to make sure you get your normal vector correct. Okay? Now, great. I have solved for the current density for the radius is equal to A. Now, I'm going to put that to the side. And that's going to be for part B. Great. Now, we can solve for when the radius is equal to B. So same thing, since we have this portion H1 and this portion H2, our N2 hat is going to be from going from the second medium into the first, and that's going to be N2 hat. And that is going to be in the negative radial direction. Alright. And what is H1? Well, for H1, that H field is going to be due to the effect of the magnetic field when the radius is equal to A. Right? So we're going to be using this E equation right here from what we solved earlier. But instead of R here, we'll put in B. So I'm going to erase that. So I'll show you here. We have the B field is equal to mu naught alpha A to the fourth 4, and instead of R we'll have B, and we put in B because the radius is going to be equal to B there, right? And if I divide by the free space permeability, I'll have the H field divided by 4B, and that's going to be H1, right? So with that being said, I'll write that into our formula. So we have H1 already, alpha A to the fourth divided by 4B, right? The radial direction, minus, and what's the H field on this side? Well, we already know that the magnetic field in H2 is equal to 0 because it's a grounded shield. So the H field is also going to be 0. And that's going to be equal to the current density. And okay, so now taking the cross product, we have R hat cross V hat. And this is going to be using cylindrical coordinates. And I'll write over here R hat cross V hat. It's going to give us Z hat. And this is in terms of cylindrical coordinates. And since we have a negative unit vector R, it's going to be negative Z hat. And so negative Z hat alpha A to the fourth divided by 4B is going to be equal to our current density. Now a quick tip, let's say it was V hat cross R hat. And so, going the opposite direction, it'll just be a negative Z hat. So, going counterclockwise will be negative, and going clockwise is going to be positive. And that's just a little tip for you there. So, putting it all together, we see that we now have the current density for R is equal to B. This is for R is equal to B. Okay, great. So now we have completed the problem. And this exam problem, at first glance, does seem that it could be very stressful when you're taking the test under a time constraint. But just understanding these two basic concepts of Ampere's loop here will help you solve for these type of problems fast, because you can see that the symmetry will allow for Ampere's law to be used in an efficient manner. And from these two solutions, we can find the H field easily, since we know that the H field is equal to B divided by the permeability. Right? And another tip for you guys is to make sure to always know how you're labeling your H fields, and that you get your N2 hat unit vector correct. Because the normal vector will be pointing from the second medium into the first medium. And here I'll just go over what if I switched out the H1 H2 for when the radius is equal to B. Okay, and I'll do that in blue. So let me just make some space. Okay, so what if this was H1 and this is H2? That means the N2 hat will be pointing outwards, right? Because the second median to the first. Well, if that is the case, then that will be R hat, positive R hat, is equal to what? H1 will now be 0, or not equal to, R hat cross H1. H1 is now 0, minus, what do we have? We have alpha A to the fourth divided by 4B. The radial direction is equal to the current density. And R hat cross V hat is just positive Z hat, but we have the negative there, so it's still negative Z hat. Alpha A to the fourth divided by 4B is equal to the current density. And is that the same? Yes, it is. So great. The labeling of the H fields will not matter. It's just you have to make sure you get your N2 normal unit vector correct. Alright. And just to reiterate, after doing this problem, you should now know how to recognize Ampere's loop, how to use Amperes law, and how to solve for the current density using the boundary conditions. Thank you, and I hope to see you next time solving more EE140 example problems.